Hello and welcome to another video lesson. In today's video lesson, we're going to talk about searching and sorting algorithms. Before we jump into that, I want to note that in this video, I will be going back and forth between the PowerPoint and the code. I'm using Visual Studio Code to show you an implementation of each of the searching and sorting algorithms. So if there's a little bit of choppiness in the video, I apologize. It's because I'm jumping from the slideshow to the code implementations, and I usually cut that step out. Without further ado, I will present sorting and searching algorithms. So sorting is a tool that you can use. It's a technique to arrange and move data in a way that follows a specific ordering. And most of the time, that ordering is going to be ascending or descending. It improves user interfaces. So if you want to arrange data in a way that users can find visually appealing, it's usually sorted. And it's an intuitive way to organize that information. So for example, if you had maybe like a contacts list, you'd want to see that alphabetized. That's an ordering, that's a sorting that makes it intuitive to a user interacting with your program. It's also a pre-processing step for other algorithms, especially your searching algorithms, which we will go over later. So some searching algorithms don't work on unordered data. And so that is one of the reasons why we need that pre-processing step. So sorting isn't just about neatness, it's about performance, clarity, better decision making. Okay, so let's continue to the next slide. And before we continue, I want to talk about swapping values. So a lot of the sorting algorithms use some sort of swapping mechanism to sort the array. And just a short discussion about that. Assume one container has juice. We'll say the left container has juice, and another container has water, and that'll be the one on the right. And I want to pose a question: how would you swap the contents of each container to each other? So you have the juice and the water, and you want to swap containers, but you want the contents, or you want the containers to be the same, but you want to swap the contents of the container. So how would you do that? One way is to use another container to temporarily hold the contents of one of the containers, and then to perform the swap that way. So I have a little piece of code here where we have a container called temp, and it's going to hold the value that's stored in the first element of this array. And then we are going to put the contents of whatever's at the second position of the array into the first position. And then for array at the second position, we're going to store the value of whatever was in temp. And this means that none of the values got overwritten in this process. None of them were deleted either. So this is a common way that this is a common technique that sorting algorithms use to perform sorting. So we'll move to the next slide. And like I mentioned before, and this is a quote from the book, sorting is a process that organizes a collection of data into ascending or descending order. I have an image of a table before sorting and a table after sorting. And you'll see that before the numbers, the integers in the array were randomized in the table. And after sorting, they are in ascending order, starting from the smallest number, moving all the way up to the largest number. That's just an example, a visual. And the first sorting algorithm that we're going to go over is called bubble sort. And bubble sort gets its name because the largest unsorted value rises to the top, like a bubble in soda or in water. This algorithm compares adjacent elements, so elements that are directly next to each other, and then swaps them if they're out of order. And it keeps looping through the list until no more swaps are needed. It often requires several passes, so you're not going to get a sorted list after the first pass or the first iteration. So that's something to note as well. And then again, another image from the book. All the images that I got for the PowerPoint are from your book. Your book does have a chapter about this. And if you want to read it, feel free, but most of the information I'm getting it from the book. So this is pass one in figure 11-12. And the array starts out as unsorted. So we have 29, 10, 14, 37, and 13. That's in no particular order. It seems randomized. So after the first pass, during this iteration, 29 and 10 are compared with each other. And if we're going to sort in ascending order. So if 29 is greater than 10, then perform the swap, and then continue to the next element in the array. So this does swap, okay? So then now we have 10 swapped with 29, and now we're comparing 29 with 14, and 14 is smaller than 29. 29 is bigger than 14, so a swap occurs there, all right? So swap, and then move to the next element, and now 29 is being compared with 37, and so on and so forth, and then we get 10, 14, 29, 13, and 37. And notice that after this pass, this first pass, complete pass through the array, after we've examined all the elements swapped with each other, we're not sorted yet. So we do another pass where we repeat the steps. All right, is 10 greater than 14? No, it is not. Move to the next element. Is 14 greater than, or is 14 less than 29? That looks fine. And then it finally gets to 29 greater than 13, so perform the swap. And then after this second pass, so once we have done this a second time, then it has been sorted. So 10, 14, 13, 29, and 37 is a sorted array in ascending order. And that's how this one works. So I have a bubble sort implementation. This is how it looks in code. So here's a function specifically for bubble sort, and I'll show you how this looks in Visual Studio Code in just a moment. Where we have an array, the size of the array, it's a function that takes the size of the array. It takes the array that you wish to be sorted, and it loops for every element in the array. So it does this n times. And then it's a nested for loop, right? Because we don't want to just do this n times. We want to also compare each element inside. So the second for loop facilitates that. So it says for int j equals 0, j less than array size minus I minus 1, and we'll talk about this in a moment, j++. If the element at position j is greater than the element next to it, swap the elements. And here's that step that I was telling you about earlier with when you have a temporary variable to hold a value so that it doesn't get overwritten or deleted at any step. It's safely held onto by this temporary variable, and it aids in the swapping. Okay, so the outer for loop tells us, like I mentioned before, how many passes to make. It is the size of the array. And then the inner for loop, we have that j less than array size minus I minus 1. What's that? Well, we subtract by I because we no longer need to go into parts of the array that will already be sorted. So this is a way to kind of cut down on the work we need to do. And the minus 1 is to make sure you don't go past the array's possible positions. We don't want to go over how many elements are in the array because you're going to get an error. We're comparing j plus I, so the minus 1 makes sure that we never go over that. So that's what that's doing. And here is a lovely little bubble sort right now. Here's how it looks in Visual Studio Code. So I have a variable, a constant integer variable to hold the size of the array, and I created an array right here. And I will get this to you, so this will be enclosed in the module as well. And you can run these and experiment with these at your leisure. I will go back to the PowerPoint. So bubble sort's complexity is big O to the n squared. So it runs in quadratic time. Like I mentioned before, the outer loop runs n times and the inner loop shrinks a little bit each time. Remember, we had that minus I minus 1. So the minus 1 was so that we didn't go over the possible elements in the array. And the minus I was so that we don't go over parts of the array that are already sorted from each step. So this still, even though we have that step that prevents us from doing extra work, the number of comparisons will still add up to a quadratic number. And so the time complexity is still quadratic. So moving on to the next sorting algorithm. Selection sort divides the array into two regions, unsorted and sorted, and it repeatedly finds the maximum or the minimum, depending on what sort you're doing, value from the unsorted side and swaps it into place. So for an ascending order, we select the largest element in the array, we swap it with whatever is being stored at the last position of the array, so the very end of the array. We know now, because we did this, that the last element is the largest one, so we don't need to loop over it in the next iteration. Oh, let me change the slide. We then search for the second largest element in the array on the unsorted side, and we place it in the second to last position of the array. And we repeat for n minus I minus 1 times on the remaining unsorted array. The algorithm works backwards from the end of the array to the front of the array. And at every step, it's going to place the largest unsorted value into the right spot at the end. So the selection, here's an example from your book, figure 11-1, of the selection sort being used. So the gray elements are the elements that we are examining. They are selected as the largest element. And then the blue elements comprise the sorted portion of the array. So the part that has already been sorted, and we know that the very end of the array is sorted because we're placing the very largest elements in the last position, and then the second to the last, and then the third to the last, and so on. And that is what comprises the sorted portion of the array. So the array initially looks like this. It's unsorted, 29, 10, 14, 37, and 13. And so we find the maximum value in this array, which is 37, and we want to swap it with the last element in the array, whatever is there. In this example, they just so happen to be next to each other, which is the 13. So the 13 and 37 swap. And now we get the second largest element in the array, which is 29. And whatever is in the second to last position will now be swapped with that second largest number, and so on and so forth. And it continues until the array is completely sorted. I created a helper function that finds the index of the largest element in the array, in the unsorted part of the array. And it creates a variable to store the max index. And it loops for j equal to I, j equal to 1, j less than or equal to I, j plus plus. So what this is doing is it's starting at 1 because we should not start at 0. If we start at 0, we're going to compare it to itself. So don't start at 0, start at 1. And j less than I, where I is going to be, it's going to represent a portion to go up to. We don't want to go into the part of the array that's already sorted, so we're just going to go up to I and not continue into parts that we've already sorted. And then j plus plus, increase by 1 each time. And then check if the element is greater than whatever's stored at array at max index. So starts at 0 up here. And then return max index after you've gone through the entire unsorted section. And then the selection sort itself goes n times, and it works backwards, by the way. Remember, we want to place things at the very end of the list. We are starting backwards. So we start I at the largest value, and then we do this while I is greater than 0, and then we decrement I each time so that we move leftward onto the list. And we get the maximum index, and then we perform the swapping. So we use a temporary variable, like we mentioned we did before, to perform the swapping step. Where are you? This is the selection sort, and I put a little note here to help you keep in mind that we do not start J at 0 for finding the largest index. We don't want to do a comparison with itself. We don't want to do that. So we will go back to the slides and continue the slideshow. The complexity for selection sort is quadratic. So the loop in the selection sort portion executes n-1 times, and during that there are 3 steps that are part of the swapping process, which gives us 3 times n-1 moves. And then the loop that finds the index of the largest element executes n-1, and then n-2, and then n- however many times until the sorting space is just a single element. And this evaluates to n times n-1 divides by 2 times. And then if we combine this term and this term, we eventually do get big O of n squared over 2. And then remember when we mentioned that when we are dealing with complexity, we're able to omit constants. And in this case, divides by 2 is the constant, so we can get rid of it. And this evaluates to big O n squared. The next sorting algorithm is insertion sort. Insertion sort partitions the array into 2 sides, the sorted portion and the unsorted portion. And then at each step, the first item of the unsorted portion is placed into the correct position in the sorted portion of the array. Each item inserted is inserted into the correct position relative to the items before it. So insertion sort starts at the second element of the unsorted array, and the array starts out as unsorted. So the second element, because the very first element starts out as the sorted portion. So the very first element is deemed sorted, and then all subsequent items are not sorted. So you start at the second element of the unsorted array. Then you compare it with the elements before it, and you shift all the larger elements a single position to the right. You insert that element at the correct position, and you repeat with the next element until your array is sorted. So the book contains a sample of what that might look like. So notice how the 29 is blue in color. The blue portion represents the sorted part of the array. And like I mentioned before, the very first element is considered sorted. And then we look at the next element. And so it's 10. So we have to copy 10 in much the same way we had a temporary variable. We're doing that here where we don't want to overwrite the value that we are trying to insert. So we copy 10, and then we go to the sorted portion of the array, and all the elements that are bigger than it, we shift to the right. In this case, the 29 shifts over to the right. And then we insert the 10 at the proper location. And then we move to the next element, which is the 14. And we copy it because we don't want it to get overwritten. And then we notice that the 14 is larger than the 10, but less than the 29. So we shift the larger elements to the right, and then we place the 14 in the position between the 10 and the 29. And now 10, 14, and 29 are part of the sorted array, 37 and 13 are not, and the process continues until the array is sorted. So before I get into the implementation, there's some key differences between insertion sort and selection sort and bubble sort. Selection sort will select the minimum or the maximum, depending on what sort you're doing, from the unsorted portion and swap that into place. But with insertion sort, we take the next element and insert it into its correct position in the sorted portion. Where selection sort is making a swap, insertion sort is pushing things and then putting it in the right place. Selection sort always scans the entire unsorted region to find the smallest element, and insertion sort only scans as far back as needed to find the point that we need to insert. Insertion sort uses a temporary variable, but it doesn't use it for swapping in the way that bubble sort or selection sort does. Instead, it uses a temporary variable. I've seen it be called key. And so in this implementation, I put this is location of the quote unquote key, but I'm calling it element to sort. It's the current element that we're looking at. It's commonly called a key. It holds the current value being inserted, while elements in the sorted portion are shifted over to make space. So this is what that implementation would look like. It will take the size of the array, it will take the array that you want to sort, and it's going to loop n-1 times. We say int element to sort, array to sort I. So this is the element that we are looking to insert. And then when we say int j equals I minus 1, this is saving the location of the key or the element to sort. Then we move to a while loop. So this int j equals I minus 1 as the location of the key, this is going to, let me see if I can actually backspace here. This is actually going to take us here. So at the end of the blue part, that's what that's doing. And then we're going to move backwards. We're going to move to the left. So while j greater than or equal to 0, and the array to sort at j is greater than the element to sort, we want to shift, and then j minus minus. This while loop is going to continue until we are past the correct spot. We're one location past the correct spot. And so when we're performing the insertion at the correct spot, which would have been j, but now we're past it, we need to increment j by 1. We need to add j plus 1 to get back to the correct position. So let me backspace here. So it's going to go here, 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 and then 1 too far, and then it needs to insert. It needs to go increment by 1 to move to the right by 1 to put it in the right spot. So that's what that is doing. Let's go back to our slideshow. So remember, elements are shifted, not swapped, and only one assignment happens when we place the key or the element to sort once the correct position is found. So let me go ahead and click this. So insertion sort complexity. The outer loop executes n-1 times. The inner loop loops at most 1 to n-1 times. In the worst case, each element needs to shift down the entire sorted portion. And so this gives us a quadratic complexity, big O to the n squared. And we haven't really talked too much about it, but there are like best case scenarios for these two, and that's if the array is already sorted, then each new element slides to the right into place without shifting anybody else, and that would be linear time. But when we look at big O notation, we're typically concerned with the worst case scenario, and that is quadratic time. So with insertion sort, it's pretty good for arrays that are nearly already sorted or small arrays. So let's see, what else do we have here? So that's going to do it for the sorting arrays. The next portion of the presentation is searching. So before we talk about searching, I wanted to talk a little bit about exhaustive versus optimized search. So searching is when you want to find a specific element of the array or the list. You want to find a specific element and maybe you want to return that element, or you just want to know what the position is. Either way you're searching. There's different types of searches. There's exhaustive, which is often described as brute force, meaning that it's going to try all the options until a solution is found and there are no shortcuts. It is guaranteed to find a solution if that solution exists, and it is guaranteed to find that if it does not have a solution. So it will find it, or it will find that it doesn't exist definitely. Then there are optimized searches, and optimized searches prune unnecessary options, or maybe it uses heuristics to find the solution more efficiently. The first search that we're going to go over is the simplest type of search, where you start at the beginning of the array and check each item one by one until either you find what you're looking for or you reach the end of the list, and that is sequential search. It's also known as linear search. So you start at the first element, compare the element you're searching for to the next one. If they match, return the index, or else move to the next element, repeat it until you find it or you reach the end. And the implementation is rather simple. So here we have an array that we wish to perform the search on. We have the size of the array, and then we have a target. This is the value that we are searching for. So for I is 0, so start at the beginning of the list. While I is less than the size, don't go past the search area, the array, increment I by 1. So if the array at that location is the target, return I, and keep going, right? And if this never finds a match, then this portion here where we say return -1 is going to execute. And sequential search is considered exhaustive. It is, well, it meets every criteria for an exhaustive search. The worst case scenario is that every element in the array has to be checked. And this is big O of n. This is considered linear time. Sequential search works on any kind of data, sorted, unsorted, but it can be very slow if your data set is large. If your data set is large, you might want to do this a little differently. You might want to prune possibilities out. You want to rule things out. Our next search algorithm is called ordered linear search. It is a sequential search on an array that is already ordered or sorted. So this is an optimized version of the sequential search, but it only works on sorted data. Once we reach a value greater than our target, we know it's not in the list, and then we can just stop early. So this starts at the first element, compares it with the target. If it matches, returns the index right away. And then here's the extra step. If the current element is greater than the target, then we need to stop because it's not in the array. And this is because, again, this only takes a sorted array if the element that we are, so if our target is being compared with something that's greater already, we know that there is no use continuing because every other element is going to be greater than the target, so we can stop. So we stop. Otherwise, you can continue checking. And ordered linear search is not exhaustive. You still have to check every element of the array in the worst case. And it is also linear complexity. I'm going to escape here, and I'm going to show you what that one looks like. So here with sequential search, it's contained in the source code that I will provide you with. And here is ordered linear search. So notice it has kind of the same structure in the beginning as the sequential search, But then we have a part of the conditional where it says, else if the element that we are currently looking at is greater than the target, then return the -1. The -1 indicates that the target is not in the array, and it also returns -1 if we reach the end of the list. So let me minimize this. All right, let's go back to our slideshow. Binary search. So this is the last search algorithm that we're going to go over, which is binary search. It's one of the fastest search methods, but the catch is that the data needs to be sorted first before we can use it. It uses a divide and conquer technique in that we repeatedly divide the list or the array in half, checking whether the middle value is greater than or less than or equal to our target, and it repeatedly reduces the search range by half until the target is found or the range is empty. So you begin with a pointer to the start and the end of the array, and you calculate the middle index as middle is the start plus the end divided by 2. That gives us the middle index. You compare the target to the middle of this array, and then if the target is found, you return the index. Else if the target is less than whatever the middle is right now, search the left half. Else if the target is greater than the element that you're searching at the middle, search the right half. And you're going to repeat this process. So let's look at an implementation of binary search in C++. So the function is called binary search. It returns an integer. It is returning the index of the target if it finds it. If it doesn't find it, it's going to return -1. So it is returning an integer, whether that's the index or -1. If it doesn't find it, is just kind of up to what the target is and what the array is. So it takes an array to search. It takes the size of the array, n, and the target, the thing that you're searching for. You establish the left and the right, or the start and the end. And so the left is instantiated at 0. It's the left side, the very first element. And the right side is n-1, which is the end. And while the left is less than the right, so continue searching as long as the left boundary doesn't cross the right. Once the left is greater than the right, it means that the target isn't in the array. So while this condition is true, then the middle is going to be the left plus the right divided by 2. This is how you compute the middle index of the current search range. So right now we're at the very beginning, so it's just going to be the middle of the array. And if you find the target, so if array mid is target, then return that index and then finish, right? Else if the target is larger, if the target is greater than the middle value, then search the right half of the array. So what that's doing is it's saying, all right, so if the target is larger, then we need to only search the right half of the array. We don't need to look at the left. So we're going to change the left to mid plus 1, and this is going to eliminate that side, and it's going to cut the search space. And if the target is smaller, so if the target is less than the middle value, search the left half. And in the same way, this is going to change the right boundary to the midpoint -1. This is also reducing the search space to the left half. And this is going to continue making the space smaller by half until it finds the target. And then obviously if we don't find the target, return -1 so that we exit the loop. It's not present in the array. We need to return -1 if it is not found. So when we move on to look at binary search's complexity, binary search is not exhaustive. An exhaustive search like sequential search checks every single element one by one until it finds the target or it reaches the end. So it checks each value. Binary search skips most of the elements because we are at each step only examining one element, the middle one, and then discarding half of the array depending on whether or not the target or the element we're looking at, the middle, is bigger or less than the target. And because of this, if you have, and this is a quote from the book, if you have an array of n items, then divide one of those halves in half and continue dividing halves until one item remains, you have performed k divisions. And then recall the last module that we talked about. We had like a rule of thumb for O log n complexity. If a loop variable or the iterator increases or decreases by a multiplication or a division rather than an addition or subtraction, the time complexity is going to be logarithmic. And so binary search's complexity is logarithmic. And it's binary search itself is fast, but it needs sorted data, and it's not exhaustive. So that's going to do it for sorting and searching. So for sorting, we went over bubble sort, selection sort, and insertion sort. And for searching, we went over sequential search, ordered linear search, and binary search. And in closing, I invite you to kind of something fun you could do is to look up some of the worst sorting and searching algorithms. That's a little fun if you have the extra time. Some of those are incredibly inefficient and incredibly bad, and it's kind of funny how some of those came to be. So if you have the extra time to do that, that's kind of something I recommend just kind of doing on your own time. It's a little fun activity. And that's going to do it for the presentation. Thank you so much for listening and have a wonderful day.